Hello. So today we are doing this problem called shortest unsorted continuous subarray. So let's do this. So the problem says that we are given an integer array, and we need to find one contiguous subarray that if you only sort that particular subarray in ascending order, the whole array will be sorted. So basically we get an array that has some random order, but some part of it may be sorted, and we need to detect which part of the array is not sorted so that when we sort only that, we can get a sorted array. So what we want is the shortest subarray, the shortest unsorted subarray that if sorted will make the array sorted, right? For example, in this list here, if we sort 6, 4, 8, 10 up until 9, then the whole array would be sorted. Yeah, so that's basically the gist of it. We can have duplicates, so that's something to be aware of and to handle, right? Okay, so let's see how can we solve this. So the first idea that I had with this is just let's have a copy of this array that is sorted. And then once we have it, once we have a sorted version, let's call it snums, then we can compare it with the unsorted one and see at which point they differ, basically. That would be the start of our unsorted subarray, and at which point they stop being different and they become equal. So, and that will be the end of the unsorted array, or the unsorted subarray. So keep going, keep comparing the two until we find the point where they differ. The first point where they differ, that's the beginning of the unsorted subarray, and keep comparing until we find the point where they stop being different, and that's the end of the unsorted subarray. As simple as that. So let's do the exactly that. So first we need a sorted version, and after that we just initialize our start and end. Let's just pick -1 and -1, since these values can't be like a start and end. That way we can check them to know if we should return 0 if the array like is completely sorted, for example. And so we need to go through the array, enumerate names, and we need to check if this is different than this. So if this value actually is different than snims, so what we said is we want, let me write this down. So we want to detect, so S would be the first in this index where snims and nims differ, basically. And end would be the last index where are different, such that they are equal after that. Okay, so if this is the case, they are different, and this is the first time they are different, which means that S is still equal to -1. Then at that point we can initialize S and the end to just the value I. So basically, say we have an example where it's like this: 2, 1, 2, 1, 3, 2, right? And 4. And then the sorted version would be 1, 2, 3, 4. So we would detect they are different here. So we can right away set our start and end here. And then we'll keep going. They are still different. And so here we need to update only the end. Start, we update it only once. And after that point, we will find that they are equal. So we won't update E, and then we will just return the difference between E minus S plus 1, basically. And that, in this case, for example, will give us 3 minus 2 plus 1, which would be 2, which is the length of what we need to sort. So here, else, which is the case where we already initialized S, but they are still different. So if they are still different, we need to update the end. So let's say if they are still different, but s is no longer equal to -1, then we can just set the end. And now after that, if neither of this condition is true, we'll continue checking, because maybe there is a case where it's 4, 4, but it's like 5, and then it's like 6, for example, and then 5 here, so something like this. So we may have it sorted here, so we need to continue checking until the end, and that's why I'm not breaking here. And then at the end, we need to just return, as we said, this value. There is only one condition where we shouldn't, is if these two didn't change, that means the array was sorted. And so to check that, we just check that -1 is not in S and E. So if -1 is not in this list, that means neither of them got updated, neither S, neither E. And so if -1 is not in this, that means that both have been updated, which means we can just return this. But if that's not the case, which means one of them didn't get updated, which can happen only if this didn't run, right? So in that case, we can just return, I guess, we can return 0, but we need to handle one other case. Say, for example, so there's a case where we have just one element. That case is by definition sorted, so we need to return 0. So, and then the empty case also, that case by definition is sorted, so 0 also works. So let's just run this and see what we get. Okay, so let's submit it. Okay, so this solution passes, that's good. Now let's try to come up with another variant. So another thing that we can use, which is very clever, is, so if the array is not, so let's see what can the array look like if it's, so basically the problem says, let's see, we say we have a portion like this, and a portion like this, and a portion like this. And this portion here is sorted already. And then we have another portion here that is not sorted. Of course, these are not always the case. It may be that this is the portion that is not sorted, but this is just to give you the intuition of the solution. And let's say this is sorted already also. Now, what is our goal here? So our goal is to find the furthest point of the unsorted portion and the leftmost, so the rightmost point of the unsorted version, and find the leftmost point of the unsorted version. So that's what we want. We want the leftmost of the unsorted portion and the rightmost of the unsorted portion. Now, what can we say about the leftmost of this leftmost here? So what can we say about the rightmost of the unsorted portion, which is this, compared to this? And what can we say for the leftmost compared to this? So if this piece is sorted, that means that the leftmost of this sorted bit must be bigger than this, than the leftmost, than the max of this. Because for this to be sorted, this value must be smaller than this value. And so what we are looking for is the value of this that is small. I think this is not very clear. This is not very clear. Let me try to explain this in a different with different words. So basically what we want here is we want to find the last element of this, which is smaller than the last, than the so we want to find the last element. So we want to find the last element that is smaller than the last seen max on the left. And we want to find the last element that is bigger than the last seen minimum value on the right. So we want to find in this the last element that is bigger than the last seen min of this right, because the minimum of this should be bigger than the value here, and the maximum of this should be smaller than the min of this. So we want to find the last element that is smaller here. So in this portion, which is the left of this, we want to find the last element that is smaller than the last seen max here. And here we want to find the last element that is bigger than the last seen min on the right. Yeah, so this is basically the gist of the idea. So let's try to write that. So in order to find, so if we find the last element that is smaller than the last seen max on the left, that would be our end point here, the last one. And then if we find this one, that would be our beginning. So this will be our end and this will be our start. And so let's initialize these values. So our start would be, and we want max and min. So let's just initialize max to minus infinity and min to infinity. And then we could say, so in order to find this value, we can just iterate from 0 to n. From 0 to n for the left side, so in range 0 to n. And we are looking for the max value, so compared to the value at names I. And we want to check, we want to find the last element that is smaller than that max. So in order to find if it's smaller, we just need to check if this is smaller than the max. And that would mean we can set our end to be that value. And that's for the end. For the start, we are looking on the right side, so we can do in range of n minus 1 and keep decreasing until we reach minus 1. And our goal is to find the min here, so min of, and we want to find the biggest one, so the last element that is bigger than the last seen min. So the last seen min is this, and in order to check if it's bigger than it, we can say this. And if that's the case, then our start would be I. And at the end, we can just return the same thing we returned in the previous solution. There is only one case we need to handle, that is when if the start point did not get updated, which means it's still equal to minus 1. In that case, we can just say s, this is valid only if s is bigger or equal to the 0, otherwise just return 0. Okay, let's run this. Yeah, so it should be names. Okay, so this passes. Another solution that is still interesting. I get a time-limited exception with it, but it's still interesting to think about. So I'm just going to explain it here, even though it doesn't like pass all test cases. So that solution relies on selection sort. So what does selection sort do? Selection sort, basically we get an array, say with A1, A2, A3, A4. What we do is just start from here and look at find the minimum in the rest. Once we find the minimum, we swap it with the beginning and move this pointer and keep going and find the min and swap it with this. And move again and find the min and swap it with this until the end of the array. That's what selection sort does. So notice what I said here when we are doing selection sort was go here and then keep going to find the min among these elements. When you find it, swap. So in this solution, we are going to do the same thing, except when we find the min, we are not going to swap. We are just going to record at that point if that's like the start or the end of the unsorted list. So we are going to modify selection sort to solve the problem. So let's first write the loops that we usually write for selection sort. So for selection sort, the loop is usually something like it's for I in range of 0 to n minus 1, and then for g. So I is this one, and j is this pointer that moves in the for each I, and it started from I plus 1, right? So we start j from this here. And so in range of I plus 1 until n. Now, what does selection sort do? Selection sort checks to find the minimum, which means that it checks if nim j is less than nim of I. So that's the condition of it. So now, instead of swapping that selection sort does, we are going to do something different. We are going to compute the left and right, which are just the which are just the boundaries of our unsorted portion. So left and right. Let's initialize them to some values, and let's figure out what can we put here. So we know that the left side is going to be the smallest one. That's what basically it's the left, so it's the far left, so it's the smallest one between the previous left and this new I that we found. So basically this means that we found a portion that is not sorted. And so in order to determine whether this is the start of the unsorted version, we could just take the minimum so that we can get the far left index. And the same thing, the equivalent thing for the right index, we can just, so this means that we found a portion of the array that is not sorted. And so we could just pick the far right index to determine the end of the unsorted portion. And so we could just do max of this and j. Why j? Because you can notice here, what I'm doing is I move I, but j moves after I. So if there is an unsorted, if this is like bigger than this, that means that the unsorted portion is this entire subarray. And so the end is j, and the start is going to be compared with I. But we need to always pick the far right and always the far left, and that's why we are using max and min here. And once we are done with this, we can return r minus l plus 1. The same thing we did before. We'll just have to take care of one case. So let's initialize this. Let's initialize left to n and r to 0. And here, if l didn't change, which means it's still equal to n, then that means we didn't enter here. But if it's less than n, that means we did enter here, and so we can return this. But if it's equal to end, then we didn't enter, so the solution is 0. And yeah, this solution should pass. Yep, I need to define n first. Okay, so as I said, it's time limited. We get TLA with it, but yeah, it's interesting seeing a modification of selection sort to solve a particular problem. And just by modifying here the swap operation to do another operation, we can solve another problem. That's one interesting thing, to modify an existing algorithm to solve another problem. Yeah, that's it for now. See you next time. Bye.